Good day to you. I'm Scott Turner, and I'm a professor of biology at the State University of New York's College of Environmental Science and Forestry in Syracuse, in beautiful upstate New York. I live in America, but I'm no stranger to Southern Africa. I lived in Cape Town for several years, met my wife there, and started our family there, and I've spent quite a bit of time knocking around the fringes of the Kalahari. I still have strong ties to the region. Lately, I come to Namibia quite a lot to work on these creatures. This is a mound built by a colony of termites, macrotermes. The termites actually don't live in the mound, they live below it in an underground nest. If you work in Southern Africa, you're probably familiar with them because they're common through the savannas of sub-Saharan Africa. You might even know termites as prospecting aids because they build their mounds from soils that they bring up from quite deep horizons. If there are mineral-bearing ores down there, their mounds can be enriched in those minerals, and clever prospecting of the mounds can sometimes give useful clues to their presence. What I'd like to share with you today is some things we've discovered about how these termites use their mounds as breathing devices for their underground colonies. As it turns out, these little insects have pulled off a darn clever trick of ventilation engineering. I'm no engineer myself, of course, and I won't pretend that I know anything about mine ventilation, but just maybe these termites do. So let's find out. As it turns out, the termite colony is a little bit like a mine. If you hack into a termite mound, you won't find many termites there. That's because the termites, about 2 million of them, don't actually live in the mound. They live in a spherical nest below it, about a meter underground. That's the first way a termite colony is like a mine. There's a zone of activity located underground, far away from the atmosphere. Structurally, the nest is subdivided into about 100 small rooms called galleries. Each gallery is connected to its neighbors through a small passageway, just wide enough for the termites to get through. That's the second way the colony is like a mine. Numerous sites of activity joined by networks of narrow passageways. Each gallery contains within it a structure called a fungus comb. This consists of chewed up wood and grass that is brought back to the nest, inoculated with a special kind of mold, and the paste is built into these combs. This is where most of the digestion of the wood takes place. And here's the third way a termite colony is like a mine. Each of the termites in a colony has to breathe, just like we do. Each termite doesn't breathe much, but a couple million of them together adds up to a breathing rate roughly what you'd expect for an animal the size of a rabbit. The fungi also need to breathe, though. Add their oxygen needs to the termites, and you have a colony that breathes at about the same rate as a goat. For the colony to survive, you have to get oxygen down there to feed that respiration, and to get the waste gas, carbon dioxide mostly, out somehow. This, of course, is exactly the problem for a working mine. The safety and productivity of miners demand some turnover of air between the atmosphere and the closed passageways of the mine. That's why mine ventilation is so important. Termite colonies have the same problem to solve, but they've solved it in a darn clever way. For a long time, we thought we knew how they solved this problem. We thought they used the mound to circulate air between the nest and atmosphere, just like a mine uses systems of fans and ducting to deliver fresh air to deep parts of the mine. We just knew the termite mound worked this way because, well, it just had to work that way. And you can find all sorts of clever schemes in the literature for how this supposedly worked. One scheme, called the thermosiphon mechanism, proposed that waste heat from the colony's respiration, which amounts to about 100 watts, warmed the nest air and buoyed it up into the mound, pushing it eventually out to porous channels on the mound surface. There, the excess heat was dumped and the spent air from the nest refreshed. This newly refreshed air became denser, allowing gravity to draw it down to a chamber below the nest, the cellar, positioning it for its next circuit. Think about how a heater in the middle of a cold room will set up a circulation cell of air in there, and you get the basic idea. Another scheme, called the induced flow mechanism, supposedly applied to mounds that had an open chimney, like this one. Here it was not nest heat, but variation of wind speed in the surface boundary layer that was the motive force for airflow. Air flowing over the horizontal opening of the chimney induced a Venturi effect that drew air up and out the chimney. To replace it, air was drawn in from numerous holes arrayed about the base of the mound. And positioned in between was the nest, which had its air refreshed by this wind-induced flow. About 20 years ago, while I was living in Mafeking, I got interested in this problem, in part because it dawned on me that no one had ever actually measured the flow of air through these colonies. They'd only inferred what the flow supposedly had to be. They had to be there because, well, they just had to be there. So I rigged up a little device to measure the flows and very quickly found out that the actual air movements were nothing like what these clever stories said they had to be. This meant that our understanding of how these mounds work had to be totally wrong. And figuring out how they actually work has occupied most of my research career since then. The first thing we found is that the nest is not ventilated in the conventional way. The nest and mound constitute two air masses that don't mix well with one another. This means that models for nest ventilation that involve bulk flows of air through the nest, such as thermosiphon flow or induced flow, cannot be correct. For example, we found that air in the mound is stirred up by wind, intercepting the mound and penetrating through the mound's porous surface. The stirring is uneven. Air in the mound's superficial spaces is stirred up more by wind than air deep in the mound is. This stirring helps clear air from the mound. Air in the superficial air spaces is usually drawn up and out the upper parts of the mound fairly quickly. By our best estimate, air in these superficial spaces turns over completely about every 15 minutes or so. Air in the center part of the mound also is eventually cleared away by wind, but here the turnover is slower, about once every hour or so. Here, air is usually drawn out to the superficial spaces first before it's drawn out the top. The reverse flow rarely happens though. It's hard for air in the superficial spaces of the mound to make its way into the center. What really surprised us though was that air in the mound never seemed to make its way down into the nest. That's totally contrary to what everyone knew had to occur, and it was our first clue to the unconventional breathing mechanism the termites actually use. At this point, my colleague Rupert Soar joined the project. Rupert is an engineer, and he was interested in termite mounds for reasons probably similar to your own. He thought termite mounds might offer some interesting ideas for novel mechanisms of wind-driven ventilation of buildings. This itself was not a new idea. Architects had already been designing termite-inspired buildings like this one, the Eastgate Center in Harare, designed by the architect Mick Pierce. By the time Rupert joined the project, I'd already shown that the conventional ideas for termite mound function that had inspired these architects, mechanisms like thermosiphon flow and induced flow, didn't actually operate in real termite colonies. Rupert's idea was to take a detailed look at the structure of the internal air passageways in the mound and nest. This involved filling up the mound with several tons of plaster of Paris. Once the plaster was set, the soil could then be washed away to reveal a cast of the internal air passageways. And here's what that looks like. Rupert's ultimate goal was to reveal the structure through a process called slice and scan. This involved casting a mound in plaster and then slicing away the entire edifice, top to bottom, using a special cutting wheel mounted on an XYZ gantry. Here's a time-lapse video of the slice and scan machine in operation. Once each cut was made, each slice was photographed and then reassembled in a computer into a 3D reconstruction of the mound. It's the most detailed picture of a termite mound ever made. And here's the result, revealed as a slice-through movie of the mound. We'll come back to this with a more detailed look in a moment. First, though, I want to look in more detail at these mound casts because they reveal some important structural details. First, we see that the mound surface is porous, and the porosity is centered in numerous networks of tiny passageways we call egress complexes. These can range from fairly simple to quite extensive. The egress complexes are where termites get access to the surface to deposit soil on the surface of the mound. It's how the mound grows, but the mound surface becomes porous as a result. The egress complexes open up into numerous vertically oriented tunnels called surface conduits. Here's what these look like in the cast. Notice how the egress complexes decorate the surface conduit all along its length. Here's what the inside surface of a surface conduit looks like. Note the numerous holes. These are the inside openings to the egress complexes. The surface conduits extend the entire height of the mound. This is a cast mound where we excavated around the base. Ground level is about here, and we washed away the soil to reveal the underground cast. You can see how the surface conduits penetrate below the ground and envelop the nest, which is just behind the network of large tunnels. Looking to the mound center, the surface conduits merge into a network of large air spaces called the reticulum. These eventually merge into a large and convoluted open space in the mound center called the chimney. The chimney eventually merges into a large opening into the center of the mound, shown here in this nest cross-section. This opens into the galleries through numerous small passageways. And peripherally, the surface conduit envelope connects to the galleries in the same way. Now let's come back to that slice-through movie. Here's the upper part of the mound. Notice how the egress complexes stream out to the surface. These are areas of active building. As we cut deeper, you can see the surface conduits begin to consolidate and how they begin to interweave into the reticulum. As we go deeper still, you can see how the chimney begins to consolidate. And notice how extensive and amorphous it is. This then eventually merges into the nest. Okay, that was interesting. Let's now turn to how the mound actually works as a gas exchanger. The first thing to realize is that the nest air and mound air are two distinct air masses that mix poorly with one another. One reason for this is thermal stratification. Nest air is usually cooler and therefore denser than the air in the mound. This, by the way, is opposite to what had long been thought, namely that waste heat from the nest warms the nest air, buoying it up into the mound. That doesn't seem to be the case. Nest structure also impedes mixing of the nest air and mound air. The division of the nest into the many poorly connected galleries limits air movements within the nest. The small connections between the gallery and the chimney in the nest center and to the subterranean surface conduits peripherally further limits bulk flows of air between the nest and air. And this is just the way the termites like it, a still and steady nest environment. Nevertheless, there's a lot of heavy breathing going on down there, and this is where the mound comes in. The mound is a physiological device with a specific function, to capture wind energy to power the exchange of respiratory gases. What's remarkable about this is that the mound performs this function without powering a bulk flow of air through the nest. This seems counterintuitive. Anytime we wish to refresh the air in a room, we open a window or turn on a fan to physically replace the air in the room. Bulk flows are also the main principle of mine ventilation. That's not the way the termite colony works, though. There's no bulk flow of air through the nest. It's not so counterintuitive, really, though, because this is exactly how our own lungs work. To understand how the termite mound works, we have to be very clear about how our own lungs work. Breathing for us is not a simple matter of moving air into and out of our lungs. Our lungs are a highly branched network of passageways that end ultimately in blind-ended sacs called alveoli. The bulk flow of air into and out of our lungs actually involves only the lungs' upper respiratory passageways. That bulk flow disappears as you go deeper in the lung, though, and by the time you get to the alveoli, the air is completely still. Here, exchange of respiratory gases is by diffusion, not bulk flow. Gas exchange in the lung is therefore a three-phase process. In the upper respiratory passageways, exchange is through strong transient bulk flows of air driven by the muscles of the chest. Deep in the lungs ultimate air spaces, the air is still, and exchange is by diffusion. Sandwiched in between is a so-called mixed convection diffusion regime. What ultimately controls the lungs' rate of gas exchange is the extent of mixing across this mixed regime region. Enhance the mixing rate and you enhance gas exchange. The key to understanding lung function is therefore understanding how mixing operates there. Key to understanding that, in turn, is to realize the lung operates in the transient phase. Because this is an audience of engineers, you'll understand me when I draw an electrical analogy. The lung is an AC gas exchanger driven by transient phase convection in the upper passageways. The transients come, of course, from the intermittent activity of the respiratory muscles, driving the tidal movements of air into and out of the lung. This is in contrast to a so-called DC exchanger, in which steady bulk flows of air are driven through a system by applying a steady pressure. A fan driving a bulk turnover of air in a room, for example, is a DC exchanger. And because you're all engineers, you'll understand me when I say that what limits gas exchange in an AC exchanger like the lung is the lung's impedance. This is why breathing faster enhances gas exchange. Impedances depend upon the frequency of the transient drivers. In the lungs, breathing faster reduces the lung's impedance, facilitating the passage of oxygen and CO2 across the mixed regime region. Okay, back to the mound. The mound is also a three-phase gas exchanger like the lung. In the mound, the three phases are a little different from the lungs, but the principle is the same. The still air spaces of the nest are analogous to the alveoli of the lung. In this instance, the structure of the nest limits bulk flows of air there, and also impedes mixing of the air spaces with the mound. The wind-stirred air spaces of the mound are analogous to the upper respiratory passages of the lung. Here, there are strong bulk flows of air, driven not by muscles, but by natural winds. And sandwiched in between is a mixed regime region where exchange between the still environment of the nest and the wind-perturbed environment of the mound occurs. As in the lung, what determines gas exchange is the extent of mixing between these two air masses, nest and mound, that are normally mixed poorly. Finally, like the lung, the mound is a transient phase gas exchange system. In the mound, the transients are not the well-behaved transients of the respiratory muscles, but the messy transients inherent in turbulent wind. Like in the lung, the fascinating details lie in the mechanisms of the mixing across that mixed regime region. We're still working through the details, but we think there are two principal mechanisms that might interest you. Both involve taming the messy AC transients that exist in turbulent winds. The first involves the mound's impedance. The mound acts like a low-pass filter for the broad-spectrum energy in turbulent wind. At the surface, where the mound first encounters the wind energy is broad-spectrum, comprising transients that span a wide range of frequencies. If you follow flows within the mound, the spectrum is filtered by the mound's network of tunnels. We think the complex interweaving of the reticulum has something to do with this. In the surface conduits, the spectrum is still quite broad, with the upper frequencies being damped somewhat. Deep within the mound, nearly all these high-frequency components are damped out, leaving only the low frequencies to drive flows there. Within the nest, of course, these transients are damped out completely, leaving only the DC gradients in oxygen and CO2 concentrations, just like in the lung. Now we can see one of the mechanisms for promoting mixing. Remember that the air spaces of the nest are connected to the mound through the chimney in the center and peripherally through the underground extensions of the surface conduits that envelop the nest. Thus, the nest peripheral air spaces will be driven by high-frequency transients, while the center spaces will be perturbed by low-frequency transients. This differential driving will perturb the interface between the two air masses. Occasionally, there will be sufficient disturbance to promote a burst of microcirculation between the two. This is why we see air coming out of the nest into the mound as bursts or puffs of air. Another possible mechanism involves a resonance phenomenon. The tunnels in the mound are long enough to form resonant structures, something akin to an organ pipe. One can calculate these expected resonance frequencies. The surface conduits, for example, can be as long as 3 meters from top to bottom. Air in a pipe this length will resonate at about 20 to 25 hertz, just below the audible range. We know, in fact, that the mound has a resonant frequency. We employed a sound engineer, John Crowley, to come to our site in Namibia to measure this. To do so, he put a speaker on the top of the mound and found that the mound resonates strongly when the speaker is driven at a frequency of 20 to 30 hertz. This suggests another form of mixing, called variously acoustic mixing or Rayleigh mixing. If the column of air contains a stratified mixture of gases, driving the column at its resonance frequency will promote vigorous mixing across the boundary. You can see this here in this video. This is a plastic bottle with a stratified layer of smoke. We've illuminated it with a sheet of laser light from a laser level. The bottle itself is on one end of a long pipe, and on the other end is the baffle of a speaker. We're driving the speaker at 3 different frequencies, 4 Hz, 8 Hz, and 16 Hz. When we switch on the sound, look at the vigorous mixing that is driven by 8 Hz, but not so much at the frequencies bracketing it. This is occurring with no bulk flow of air. This is acoustic mixing at work. We think something like this might be happening in the surface conduits. Within the surface conduits, there should be a stratification of air between the subterranean parts, which communicate with the nest's peripheral air spaces, and those parts in the mound that communicate with the turbulent atmosphere. If the broad spectrum turbulent energy that we see in the surface conduits can be tuned to resonate in the surface conduits, as we strongly suspect, this could promote mixing of air between the upper and lower parts of the surface conduits, and this will promote gas exchange. So, what does all this mean for mine ventilation? That's not for me to say, of course. I'm just the biologist in the room, and you're the engineers with real problems to solve. Nevertheless, here's my 2 cents. First, as I understand it, the prevailing model for mine ventilation is what I've called DC ventilation. You use fans, ducting, and plants for cooling and filtering to drive a bulk flow of air through the air spaces of the mine. When you consider that mines contain a lot of dead-end spaces, just like the lung and termite colony does, you end up with dead zones, poorly ventilated regions that can produce detrimental conditions for the health and safety of miners working there. Lungs and termite mounds teach us an important lesson for how to deal with these dead zones, though, and perhaps there's some inspiration there for dealing with dead zones in mines. These might involve supplementing DC ventilation schemes with AC exchange mechanisms. There may be a lot of potential there. In my conversations with other engineers, I get the impression that this is a largely unexplored area of ventilation engineering. At a mine face at the end of a long passageway, for example, perhaps infrasound could be used to power mixing of that dead space with the broader ventilation schemes of the mine. In the same way, acoustic mixing seems to operate in the termite mound. It wouldn't be a complete solution, of course, but it may make standard ventilation plants more efficient. An alternative would be to drive different parts of a mine's airspaces at different frequencies, exploiting the natural impedances one might expect in a network of mine passageways. This, too, might enhance mixing of dead spaces in a mine network with the broader ventilation schemes of the mine. Nevertheless, this is just a biologist speculating wildly on things that you, the engineers, are in a far better position to be thinking about. And with that, I think it's time to move to the Q&A so that your expertise can be brought in. So I thank you for your attention, and on to the Q&A.